I thank the organizers for inviting me, and I also very much thank the Boeing company. The flight I took was from Newark nonstop to Cape Town, and so they make a very reliable airplane that functions perfectly for 14 hours. The return flight will be 16 hours. So I'm going to talk about Rossby-wave instabilities in disc. This was research done at Los Alamos with Wee Lee and Sterling Colgate, and it's turned out to have some important applications that I will discuss. Rossby waves are very unusual waves, and they're almost everywhere. And on the Earth, they're important for the mixing of cold and hot regions of the Earth's atmosphere, and they're very peculiar waves. On the surface of the Earth, in the atmosphere and the oceans, the phase velocity is in the westward direction, and the group velocity is in the eastward direction. So this is a very unusual type of wave. That's also important for in the dynamics of accretion disks. And so our work on this topic was really the first in the area of accretion disks, where the Rossby wave is quite important. Oh, I'll give you a simplified discussion of how these form. The initial theory was done analytically, and the basic equations are continuity equation, the Euler equation, and a constant entropy equation. And so we take an equilibrium disk and do standard perturbations, and this can be reduced to a Schrodinger-like equation for the enthalpy perturbations, which I show here. And it turns out that the key function here is the inverse vorticity in the flow, curl of u in the denominator, and it also, this is the key function for the waves. And I show a sketch in the middle of showing the profile of this inverse vorticity and the wave function. And so if the bump in this inverse vorticity is large enough, then the wave is trapped. The Rossby wave is trapped in this region. And the diagram at the bottom shows the trapped wave. So by solving the Schrodinger equation, the solution will give you the growth rate of the instability. And so this analytic theory showing in more detail the Schrodinger equation and the effective potential a lot of details, but there's evidently a region where the wave can be trapped. And the condition for trapping then gives you the growth rate of the instability. So then I'll move to simulations, which for the most part agree with this analytic theory I indicated. So we look at a case on the left where there's a bump in the density, and here it shows the disk profile, and depending on the initial conditions, you can start with 3 vortices. The vortices are anticyclonic, and as a function of time, the vortices tend to merge and form a single vortex that's shown on the right-hand side. So here I'm showing in more detail the streamlines. On the bottom here, you can see there's the anticyclonic vortex. And we've also done this with the case of a magnetic field. Magnetic field tends to be twisted by this vortex. And here I'm showing work by Varnier and collaborators, the effect of the poloidal magnetic field. And one of the important aspects, it turns out, that these anticyclonic vortices are very effective in trapping dust. And the reason for that has to do with the fact that there's a pressure maximum at the center of the vortex, and the dust that is outside of this vortex is going with Keplerian speed, but the gas is actually going more slowly because of the pressure gradient. And as a result, the dust on the outside tends to drift into the center of the vortex, and the opposite arguments apply on the inner side of the vortex, and the dust tends to drift to the center of the vortex. And this has been observed in many sources now. The first was Ophiuchus 48, and showing the ALMA image of the dust emission for this source, which is accumulation of dust. And so many examples of this. So the origin of the bump in the density, one of the possibilities is you have a planet, a Jupiter-sized planet, and the disk equilibrium has bumps in the surface density, and those bumps then are very good at generating these vortices, and the vortices trap gas. And so there's been many studies in this area. One notable one is by Zhu and Stone, showing numerical simulations of dust trapping in the vortices. So here are some more examples of dust trapping. One of the things I'll mention is that the recent studies of the general relativistic hydrodynamics around a black hole shows that the definite signature of Rossby vortices at the innermost stable orbit in these systems by Varnier, Vincent, and Cassie. And so this is ongoing work. This is, I think, a paper of 2020. And with that, I will conclude.
Thank you very much.